So, let us start a new subject or rather a new module in the study of quantum mechanics that we have been engaged in, and it is called as the quantum computing, and possibly it is one of the most interesting topics that will keep the scientists busy over the next decade or so, because there are lots of developments that are happening and lots of open problems which need to be solved and attended. So, in this particular lecture or this section of the lecture, I will give a brief introduction to this quantum computing, and sort of this will be more like a popular introduction, which should be acceptable or rather understandable for more general public. And then we will go on to the details of various subtopics that we will mention in this lecture. So, once again we go back to this Schrödinger's cat, which we have talked about earlier. So, just to remind you of this situation, that there is a cat which is left alone in a room and nobody is watching it. There is a hammer that you can see, which is hanging on a green colored portion kept in a bottle, and this hammer is connected to a pulley. So, if the cat comes and disturbs the pulley, the hammer will fall onto the glass tube, and the portion will come out, and the portion is assumably poisonous. So, the cat will die, and if it decides to stay away from it, then it will be alive, and if it does not tamper with the pulley, then the hammer will be where it is, and there will be no spilling out of that poison, and it will be safe. So, unless one does a measurement, one does not know whether it is dead or alive. So, it is in the superposition of state in the mind of an observer before an observation is made, and so it is in a state which may be given by a superposition, a superposed state, which is a psi alive plus a psi dead. And just to have proper normalization, we can write 1 by root 2, so that the probability of being it alive is half, and the probability of being dead is also half. Now, as soon as one does a measurement, it collapses into one of the available states, which is either dead or alive, and say it is alive. Then the amplitude that is associated with alive becomes 1, and the other amplitude that is associated with the state dead is equal to 0. So, as long as one has not made any measurement, it is in the superposition of state. Let us talk about this coin, tossing of a coin, unbiased coin. So, it will be when it spins, goes up and then comes on to the ground, either between your palm or on the ground, it is found in one of the states, that is head and tail. So, once you make a measurement, once you want to decide say who would bat first in cricket, it collapses into one of these head or tail. So, a quantum mechanical coin in a sense is always spinning, because it is in the superposition of state and never comes down. The moment it comes down and you make a measurement, it becomes classical. So, measurement actually in some sense kills quantum mechanics. Now, so there are various such examples of these two state systems, just like it is mentioned here, and we have given the example of coin tossing giving head or tail, or it could be just the two states of a spin half particle. Which are given as up, down, or take as the on off state of a switch, or it could be the ground voltage V equal to 0 and an excited voltage which is say V equal to some V. So, 0 and V can also be taken as a two state system. So, we will show that this two state system and the superposition that goes along with it forms an important part of this quantum computing or the quantum information as the name goes. So, we will discuss what are called as qubits, which are nothing but just an amalgamation of the two words quantum and bits. Bits we are familiar in the context of classical computers. Bits are 1 and 0 and every number is formed by the combination of 1 and 0. And when we discuss it in the context of quantum mechanics, then it is called as qubit. So, we are talking about particularly two level quantum system. We can actually talk about multi-level quantum system, which we just briefly will touch, but two level systems are most important and convenient for us to discuss. So, as we have just said that there are two level quantum systems, many of them such as photons having the polarization of photons, the spins of the electrons, the nuclear spins and a large variety of them as we have just seen. So, let us just draw two coordinate axes and label them as 1 and 0. You can also label them as dead or alive, you can also label them as up or down in the context of the spin half particles, but let us just talk about 1 and 0 just like the classical bits are being introduced. So, these zeros and ones are the computational basis states which are going to be useful for our discussion. So, we are just looking at a vector which is formed by the combination or the superposition of 0 and 1. Just recall that we have written down a state like this in the last slide of the cat being dead and alive. So, the 0 say corresponds to dead and the 1 corresponds to alive with their individual amplitudes given by alpha and beta. And so, this is a vector that is drawn in that space which is spanned by the 0 and 1 cats. There is of course, a normalization condition which is what we have seen. There is a half possibility of the cat being dead and the half of it being alive. So, the amplitude square should be normalized, that is the alpha mod alpha square plus mod beta square should be equal to 1. So, this is a statement made by Richard Feynman. He said that all we do is draw little arrows on a piece of paper. So, you see that with 0 and 1, one could write a unique classical number which is usually the numbers that are fed into the classical computers that we all are familiar with. However, in this particular case there can be infinite number of numbers that can be formed with different choices of alpha and beta, the only constraint being alpha square plus beta square or the mod alpha square plus the mod beta square equal to 1. So, say for example, alpha equal to or alpha square equal to 0.99 and beta square equal to 0.01 would give rise to a particular state, and another distinct state can be obtained by taking alpha mod alpha square equal to 0.98 and mod beta square equal to 0.02. So, they are distinct quantum states and could be made to carry distinct information. Okay? And there are infinite number of such combinations that are possible. So, just by using the bits 0 and 1 in a superposition sense, we can actually build an infinite number of, or rather store infinite number of numbers. So, in some sense let us talk about a postulate or rather a piece of information which is important in this context. So, is associated with any quantum system there is a complex vector space known as state space. Okay. And the state space that we are aware of are all complete, which means they are orthogonal to each other, each entry is orthogonal to the other and they are also normalized. So, they are orthonormalized and in that sense they are complete. And an infinite vector space has a special name which is called as a Hilbert space after the name of a mathematician called Hilbert. The state of a closed quantum system is a unit vector in the state space, just as in the slide that we have seen that this is that vector. So, a state of a system is represented by this vector which is alpha 0 and beta 1, where clearly the 0 and the 1 form the coordinate axis for this particular problem. We will of course mainly work with qubits as I told. So, which have a state space which we write as C 2, because these are complex vector spaces. So, we write it with a C which denotes a complex vector space and 2 denotes a 2-dimensional complex vector space. So, a qubit alpha and 0, alpha on 0 and beta on 1 is actually written by a 2-column vector which is alpha beta. So, this is a notation that is somewhat universally accepted, and one can simply write within a like a column vector alpha beta. It would mean that we are talking about a qubit with amplitudes alpha and beta corresponding to the 0 and the 1 states. A few more conventions if would actually help us to understand things better. So, we write vectors in state space as psi, okay, which is equal to alpha multiplied by that 0 ket plus the beta multiplied by the 1 ket. So, this is called as a ket notation which you are aware of, and we nearly assume that all our physical systems are finite dimensional state spaces. Of course, for the sake of learning quantum mechanics, we have seen that they are actually they could be infinite dimensional. In fact, all these x and p, the position and the momentum, the basis in which they are written are actually infinite dimensional, but for our the needs for this particular subject, we can think of finite dimensional state spaces, and they are orthogonal, orthonormal to each other, and not only that, if they are not orthogonal, they can be orthogonalized by a technique which is called as a Gram-Schmidt orthogonalization. So, we can actually think of a d-dimensional space instead of a 2-dimensional space, and we can write down a state space or a state vector psi as alpha 0 0 and alpha 1 1, alpha 2 2 and all that, and all the way going up to alpha d minus 1 multiplied by the ket d minus 1, and in our shorthand notation it will be alpha 0 alpha 1 alpha 2 and all that to alpha d minus 1, and as we have learned earlier that this corresponds to a d-dimensional complex vector space. So, this is called as a qdit instead of a qubit, dit for a d-dimensional space. These concepts of quantum entanglement and various other things would be elaborated later in the next lecture or in the next discussion, but let us a priori define them and try to at least get ourselves motivated that these are important things to study in the context of quantum information. So, quantum entanglement is a uniquely quantum mechanical phenomena and has no classical analog. I mean, this is what it means. It is a property of a multi-qubit, which is a tensor product of individual qubits, and can be thought of as a resource in quantum computing. The key to entanglement is the property that the state space cannot be decomposed into component spaces. So, the composite space remains composite and no combination or rather no choices of some complex coefficients, we would be able to write that as a product of two spaces or two qubits. So, in summary, if we want to just say before we do things in details, in summary, by measuring one qubit, it is possible to affect the measurement of other qubits or qubits in the system. And this also has relevance to EPR paradox. EPR paradox, these EPR are the first letters of the names of Einstein, Podolsky and Rosen. And these are, so Einstein actually questioned that can quantum mechanics be complete, because this quantum entanglement actually gives rise to the possibility of faster than light communications. And since relativity clearly states that there can't be anything which moves faster than light, so is quantum mechanics is in confrontation with relativity and whether it is complete. And Einstein had this idea of that there are hidden variables, however, they are negated by Rosen and by the Bell's inequality. There is another very interesting concept in in physics which has found a lot of mention in the science fiction books and movies. It is called as quantum teleportation. So, quantum teleportation is about carrying a fixed amount of information through the system of qubit. So, this certain amount of information is being carried, okay? And basically this, if this transmission of information happens at a speed which is faster than the speed of light, then we can say that there are a teleportation of information that happens, and it means that to replace a state of one qubit with that of another. Okay. And the interesting name, of course, the name is very interesting, it is called quantum teleportation. This name is derived from the fact that the state is transmitted by setting up an entangled state space of 3 qubits and then removing 2 of them from the entanglement via measurement. Well, of course, these let them remain as words, a little complicated that too. However, we will make sure that one understands what is being conveyed here. So, since the information of the source qubit is preserved by this measurements, the information lands up in the third, that is the destination qubit. So, this is all about quantum teleportation, and you would find them, as I said, that mentioned in the science fiction movies or books. Then we would also discuss what is called as a super dense coding, which is in some sense it is the reverse of quantum teleportation. So, the idea is to send 2 classical bits of information by sending 1 quantum bit or qubit. So, it works by first pre-communication of this EPR pair. So, EPR pair are those variables which when one being determined, the other automatically gets determined, that is called the EPR pair, that is shared between the receiver and the sender. Let us just introduce the quantum logic gates, which are analogous to the classical logic gates. So, if you have a quantum NOT gate, so an input qubit would pass through a quantum NOT gate and would give me, so if it acts on a 0 will give me 1, and if it acts on a 1 it will give a 0. So, the output qubit will be, if the input qubits are 0 and 1 as it is written on the left hand side of those 2 equations, then the output qubit would be what appears in the right of those equations, that is namely 1 and 0 corresponding to 0 and 1 qubit. So, the question is that now if we want to do this operation on the on a qubit which is given by a combination or a superposition of alpha 0 and beta 1, then what happens? So, alpha 0 actually goes to alpha 1 and beta 1 goes to beta 0. So, one actually gets the interchanging of the probability amplitudes or the amplitudes of this state spaces. So, the matrix representation of such a thing can be written as 0 1 1 0 and so that the 0 is converted into 1 and 1 is converted into 0 and so on and so forth. And this is nothing but if you see that this is like a the Pauli matrix, the x component of the Pauli spin matrix corresponds to spin equal to half. And so, the general dynamics of closed quantum systems including the logic gates can be represented by unitary matrix. We have given the definition of unitary matrix. Unitary matrix is defined as U T U or U dagger U is equal to an identity matrix. So, that is the definition or rather that is the test for a unitary matrix. So, let us look at this the Pauli gates which are sigma x or sigma 1 and that just acts like a NOT gate. So, it converts 0 into 1 and 1 into 0 and also there is a y gate which is written as sigma y or sigma 2 and this has a particular form which is 0 minus I 0. Do not mistake any of these having complex entries to be non-Hermitian operators. They are all Hermitian operators, they have real eigenvalues, so one can check that. So, this is a y gate also known as the sigma y or sigma 2 as I told you, and there is a z gate also known as sigma z and sigma 3 and that is just returns back the states excepting for the one state it returns a minus 1. So, it is written as 1 0 0 minus 1 and this is nothing but the z component of the Pauli matrix. Okay. So, as an exercise you can actually show that that x into y is equal to I into z. So, this take this matrix and multiply it with this matrix. So, let us do that for the moment. So, x y equal to 0 1 1 0 and 0 minus I 0. So, this is equal to 0 and I. So, then 0 minus I and 1 0. So, this is equal to 0 1 0, this is also equal to 0 1 minus I. So, this is minus I and this is equal to I and this is 1 0 0 minus 1. So, this is I into z okay. And so on. So, these are easy things and there is also another a 2 by 2 matrix which is of importance here, that sigma 0 which is equal to the identity matrix, and it is important for you to know from the mathematical point of view that any 2 by 2 matrix, call it A, B, C, D, they can be written in terms of sigma x, sigma y, sigma z and sigma 0 by properly choosing coefficients, any 2 by 2 matrix. Also as an exercise one can show that the x square equal to y square equal to z square equal to an identity matrix. So, let us give a very brief introduction to the quantum computing power and why quantum computers will take a center stage in research and in learning for the next maybe a decade or even more than that. It is because the integer factorization, which is impossible for digital computers to factorize very large numbers, which are the product of 2 primes of nearly equal size, and a quantum computer with 2n qubits can factor numbers with lengths n bits, which are binary lengths. Quantum database search, as an example, one can see that to search the entire Library of Congress for a particular name, given an unsorted database in classical computers, it will take 100 years, whereas in a quantum computer, it should take half a second, and that is a miraculous speed that we are talking about. So, what is a quantum computer? A computer that uses quantum mechanical phenomena to perform operations on data through devices such as superposition and entanglement, which is a little of it we have already seen. We will see more of that. And classical computer, as opposed to the quantum computer, it uses voltages that flow through circuits and gates and can be calculated entirely by classical mechanics. So, one of the very important thing about quantum computation is factorization of very large numbers. And there was an algorithm put forward by Peter Shor, in which this algorithm is used to factor numbers into their components, which can potentially be prime, just like as we have seen just a while back, and it does this in roughly order of n cube quantum operations. Okay. So, the best known classical algorithms are at the best exponential. Since the difficulty of factoring is believed to be exponentially hard, it forms the basis of most crypto systems. Okay. Thus, factoring in polynomial times so basically because the quantum computing does it in polynomial times, which is n cube, it has attracted a significant amount of attention. Let us look at this Grover's search algorithm, which says that in some sense, the parallel version of the classical computer is already inbuilt into that. So, if you want to understand how the classical computers work, they actually work with a flow in time, which means that one job gets over and the next job starts. Like if you think about the multiplication of two large matrices, it will multiply the row of the left one to the column of the first of the second one, and then store it as the first element, sum all these entries and store it as the first element of that resultant matrix, and then it will go on to do it for the second row and the second column. However, all these things are done in a parallel fashion in a quantum computer. Let us see how that happens. So, let us say that I am thinking of a number between 1 and 100, and say I have thought about a number which is 3. So, the classical computer will keep asking that is the number 1, is the number 2, is the number 3, is the number 4, and all that, and then once it gets the answer yes, it stops its operations. So, it is like this, the classical computer you keep going 1, no, 2, no, 3, no, and so on. So, there will be n such queries by which it will be resolved that actually the number that I have thought about is 3. However, in a quantum computer this is done very differently, where it is put as the entire 1 to 100 is put as a superposition, and so there is an input that is given to the quantum computer is 1 plus 2 plus 3 plus 4 and so on. And so, it will keep doing it no, 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 and then yes for third, and then no, 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 and for the rest 97 entries or 96 entries. So, this is called as a Grover search algorithm. So, the quantum computer will find the answer to the query in very lesser number of queries as compared to the classical computer. So, the practical quantum computer applications is that the quantum mechanics simulations in physics, in chemistry, material science, nanotechnology, biology, medicine, computers can simulate millions of variables at once, and all are limited today by the slow speed of the quantum mechanical simulation. And then there are something called as crypto analysis, they are capable of cracking extremely complicated codes, and this RSA encryption, as the name goes, and typically uses numbers with 200 digits. So, let us have a brief look at the history and the main ones in fact. So, this is the quantum computing history. In 1993, Alexander Holevo published a paper showing that the qubits can carry more than classical mechanics classical bits of information. 1981, Richard Feynman determines that it is possible to efficiently simulate a evolution of a quantum system on a classical computer. 1985, David Deutsch of the University of Oxford described the first universal quantum computer. 93, Dan Simon at Montreal invented an oracle program or problem for which quantum computer would be exponentially faster than the conventional classical computer. This algorithm introduced the main ideas which were then developed in Peter Shor's factoring algorithm. We will give a detailed account of this Shor's algorithm and Shor's problem, the factorization problem. 1994, Peter Shor at AT&T Bell Labs discovers an algorithm to allow quantum computers to factor large integers quickly. Shor's algorithm could theoretically break many of the crypto systems in use today. In 1995, Shor proposes the first scheme for quantum error correction. In 96, Grover, which is we have mentioned his work at Bell Labs, invents a quantum databases search algorithm. So, that is the Grover search algorithm. In 97, David Corey, Fahmy, Timothy Havel and Gershenfeld and Aizheng Chuang published the first paper on quantum computing. So, it is not very old, it is about 20-21 years old when the first paper had come out. 98, the first working 2-qubit NMR computer demonstrated at the University of California at Berkeley. 99, first working 3-qubit NMR computer demonstrated at IBM's Almaden Research Center. The first execution of Grover's algorithm was achieved. In 2000, first working 5-qubit NMR computer demonstrated as IBM's Almaden Research Center, and 2001 first working 7-qubit NMR computer demonstrated as IBM's again Almaden Research Center. And of course, these activities are going on. It has not stopped at 2001, but I have just given a brief history of that, how it developed in the initial days. So, what are the quantum computing problems? The current technology or the 40-qubit operations operating machines needed to rival current the classical equivalent. Errors are posed by the decoherence. There is the tendency of the quantum computer to decay from a given quantum state into an incoherent state as it interacts with the environment. Interactions are unavoidable and induce breakdown of information stored in the quantum computer, resulting in computational errors. And error rates are typically proportional to the ratio of the operating time to the decoherence time. So, that is the errors rates, or one can estimate errors by that, and the operations must be complicated much quicker than the decoherence time. So, these are some of the problems that are going to come up or that have already come up. However, there are also efforts to negotiate or mitigate those difficulties and problems. So, with this I will end this somewhat popular introduction to the quantum computing. However, I will take on the each of the topics or most of the topics in details for a better understanding of the subject.